This is the first in a series of videos on energetics suitable for IGCSE chemistry, and hopefully at this point you've got a basic understanding of what an exothermic and an endothermic reaction is. And a very simplistic understanding is that an exothermic reaction is something, or is a reaction, a chemical change that releases energy. And it releases energy, and that energy goes into the surroundings, and it causes the temperature of the surroundings to increase. They get hotter. And there are numerous examples I can think of exothermic reactions. Combustion is an exothermic reaction, burning things, burning methane in a Bunsen burner, on your gas hob at home in the kitchen. Neutralizations are often exothermic reactions. Reacting magnesium with oxygen is an exothermic reaction. So these are reactions that give out heat, they release energy, and they increase the temperature of the surroundings. And the opposite to these are endothermic reactions. These are exactly the opposite. They're reactions that absorb energy from the surroundings, and as a result the temperature of the surroundings goes down. They get colder. And so while there aren't quite as many obvious examples of these, very good example is the reaction used in cold packs or ice packs, which you see in sport. So for injuries, for sprains, inside those ice packs you get an endothermic reaction going on, and they are very, very cold. So this is a practical example of an endothermic reaction. Thermal decompositions are often endothermic reactions. So in the blast furnace we rely on the thermal decomposition of calcium carbonate, which breaks down to give calcium oxide and carbon dioxide, and that's an endothermic reaction. It needs a large amount of energy to break up the calcium carbonate substance. Now let's look in a little bit more detail at these two types of reactions. Before we go any further, I'm going to compare a chemical reaction to a romantic comedy. Over the years I've been dragged to the cinema to see a number of romantic comedies. I'm just mulling over whether I actually enjoy a romantic comedy. I think I probably do. And it seems to be that there's a bit of a trend with some of these, that the early part of the film, it's very sad, it involves the breakup, and in the latter part of the film there's the makeup, and everyone leaves the cinema feeling happy and fulfilled and ready to go on with the rest of their lives with a smile on their face. And the same is true of a chemical reaction. Let's imagine we are reacting hydrogen and chlorine to form two lots of hydrogen chloride. So at the start we have hydrogen molecule and a chlorine molecule, and very upsetting, the molecules break up. Now in order to break the bonds we have to pull the atoms in the molecule apart, and this takes energy, so we have to put energy into the reaction. The opposite happens when we are making bonds. We are fixing two atoms that previously were wandering around all over the place together, so they are held now in position, bonded to a partner, if you like. And so whilst it took energy to pull the original molecules apart, when new bonds are made, energy is released. So all reactions have two parts. They have the breakup at the start when we put energy in, and they have the makeup at the end where energy is released. And the amount of energy that goes in the breakup and comes out in the makeup determines whether the reaction is exothermic or endothermic. And we can show this on a diagram, and this is what's called an energy profile diagram. So on this axis we would label this energy, and that's measured in kilojoules per mole. And on this reaction you can think of it as the progress of the reaction, a bit like time but not quite as specific as that. And here we've got the reactants. Okay, now if you're asked to do this in an exam, they'll probably give you a specific reaction, and you need to write the specific reactants on that line there. This level here is the products. So again, if you were given a specific reaction, you need to write the specific chemicals on that line there. And what you can see in this reaction is that the energy of the chemicals increases. And so at the start here, at step 1, this is where we've got the breakup going on. This is where energy is going into the system to pull the old bonds apart. So the breakup, we have energy in, and in actual fact, well, the breakup bit is an endothermic process. When the old bonds are broken, now new bonds can be made. So here we have the makeup. New bonds are being made, the line is coming down, so energy is coming out of the system, so energy out, and that is an exothermic stage. Now, you can see here that this reaction has an endothermic part and an exothermic part, but is it endo or exothermic overall? Well, you can see quite clearly that the endothermic part of the reaction is bigger than the exothermic part of the reaction. So overall, I'm going to draw a line from level with where the reactants are, make the line a bit bigger, up to the products. Overall, the energy of the system goes up, so it's an endothermic process. The energy needed to break the bonds is greater than the energy released when bonds are made, so overall the reaction is endothermic. And this is an energy profile diagram for an endothermic process. Okay, we'd expect the temperature in this of the surroundings near this reaction to go down. It's going to get colder. And you would be expected to draw this in an exam. Make sure you label the axes, okay? Make sure you label the reactants, the products, and if it's endothermic, the products are on a higher level than the reactants. This is an exothermic reaction. So here we label our reactants, we label our products, and on this axis we're going to label energy and its units, kilojoules per mole. And we can see here in stage 1, that is where we get the breakup. Oh, so sad. Okay, the old bonds are breaking up, and in order to pull the bonds apart, we have to put energy in. It's an endothermic step. But when the old bonds are broken, the new bonds can be made. And at this point, I call it the makeup. It would help actually if I labelled it, wouldn't it? There's number 2. Here's the energy coming out. Okay, and that's an exo step. So, what makes this reaction exothermic is that the energy absorbed to break old bonds is less than the energy released when new bonds are made. Therefore, overall, the reaction is exothermic and the temperature of the surroundings increases. Now I should also mark delta H on this diagram. So it comes level from the reactants, delta H. Dreadful writing, but it goes down level with where the, oh good grief, with where the products are. And this is a very popular exam question. They often ask you to draw an energy profile diagram for a reaction, and then they often ask you for 3 marks to explain why the reaction is endothermic or why it is exothermic. So, to summarise, an exothermic reaction causes the temperature of the surroundings to increase because the energy absorbed to break old bonds is less than the energy released when new bonds are made. And therefore, overall, energy is released. And you could show that diagrammatically on one of your energy profile diagrams. The endothermic reaction causes the temperature of the surroundings to decrease because the energy absorbed to break old bonds is greater than the energy released when new bonds are made. So therefore, overall, energy is absorbed and the temperature drops. Now, one thing I haven't explained here is the symbol delta H, which I used on the previous slide and the slide before that on our enthalpy profile or energy profile diagrams. H in energetics could stand for heat energy, but technically speaking we should use this word, and maybe I should have used it throughout this video, enthalpy. And enthalpy is just a very posh word for heat energy. So whenever you hear a chemist refer to enthalpy, what they're actually talking about is heat energy. And if you see the symbol delta H, that just means, well, delta often means change, so that just means change in enthalpy, or the change in heat energy. And that's occasionally asked as a 1 or a 2 mark question. So what does H stand for, or what does delta H stand for? So if it says what does delta H stand for, ensure you explain the delta, which is change, as well as explaining that H stands for heat energy. And it's often measured in kilojoules per mole. That's one of the worst J's I've ever seen. And that's the end of the first video on energetics. In the next video we're going to look at applying these principles to calculations.